people that he likes, the ones that actually do well in chemistry.
All right, who has completed the homework? Really?
Yeah.
Done?
Yeah.
Okay. Who needs a little bit of extra time?
I mean, I can do it all.
Can I get an extra point?
Just one problem.
What time do we have class? 11 o'clock. 11 o'clock on Monday. No later. Okay.
Dr. McGuire,
Yeah.
are we going to do Fisher projections in
They're not going away. We're going to do a couple of weeks on that molecule.
sugar?
I haven't really had time doing Fisher's projections using the software. It's probably dumb, right? But
So like Fisher projections into anything other than Fisher projections.
like, can you just share like a quick or do you have more? Or like something?
Just do this, and then won't leave the room until Fisher projection. You say solvolysis?
No, it's the software.
Oh. Yeah. Okay. Absolutely, because that's a couple of questions on the homework. Yeah. Okay. Let's stick with this. I thought you dropped. There was a really vicious rumor going around that you had dropped class.
This class?
Yeah.
Okay.
I started it.
Well,
1 minute late.
I still have the rest of today to do it.
Oh yeah, you could do it. You did it.
So I have said to a number of students already this week, I am happy with the way that the week has started. Because my office hours and the other hours when I'm actually in the office hours, but it's not an actual office hour, have been filled. That's why I have them. You should come and ask. I would much, much rather that you come and pester me and ask than suffer quietly and then come and demonstrate that you're struggling. Just come and ask. Come and ask. Okay, we've done eliminations. We've done electrophilic additions. And that leaves us with the other big mechanism from organic 1 that was
Nucleophilic substitution.
nucleophilic substitution. Okay. In a substitution, do you change the amount of saturation that's in the molecule? No. You don't go from being saturated to being unsaturated. That would be an elimination. And you don't go from being unsaturated to being saturated. That would be an addition. What you do is you just replace something that you have with something that's better. Which means that there has to be a leaving group. That leaving group must contain a weak bond. Your product just changes out that weak bond for something that's better. Okay, and we can design in the weak bond on purpose. It's probably why we did the electrophilic addition in the first place. We have an alkene. Okay, that's great. What can we make out of it? I don't know, maybe we could make something else. Oh, why don't we put a leaving group in there so that then we can do something else with it at a later date? So that's a tactic. We build in molecules that have weak bonds so that we know that we can replace them later on with other things that we actually want. Okay. Give me an example of a bond that is weak.
Hydrobromic acid. HBr.
Okay. So in HBr, that bond is very, very polar, but there's no carbon here. So my reactant number one is the thing that normally holds my carbon chain. Here's my carbon chain. Is the carbon to carbon bond weak? No. We very seldom break the carbon-carbon bonds. When a carbon-carbon bond breaks, that's noteworthy. The book will make a big deal out of it. I will make a big deal out of it. It's not going to happen very often. So we're going to have to build in a bond to something X. What is it that I can do that makes the carbon to X bond be weak? And I'm just working on the pure assumption that when people put a 24-pack of Play-Doh in the room, it's automatically for me.
It's for D-bio.
It's D-bio. We ran out of time.
You're gonna run out of Play-Doh. How come biology has a budget that can buy Play-Doh?
Dr. James had it hidden somewhere because someone took Dr. Hoffman's. That's what I got told yesterday.
It's Play-Doh. The carbon to X bond needs to be weak. How do I make it, how do I guarantee that it's going to be weak? What type of atom should X be? Should it be a hydrogen? No, why not? Yeah, it's going to be something from the right-hand side of the periodic table. It's going to be something electronegative. Why? Because if I make that bond polar, then the electrons have already started the process of giving up. This bond is polar. The electrons, in the simplistic theory of what electronegativity is, are spending more time at the other atom. chlorine would be a good choice for a leaving group. What could possibly be better than chlorine? Bromine. Why would bromine be better? It is not more electronegative. Electronegativity increases as you move left to right and bottom to top. So chlorine is more electronegative than bromine, and yet bromine is a better leader group. Why? Bigger. I was teaching a class the other day and we were talking about atomic radius. If the radius of an atom is this big, and the radius of the other atom that it is bonding to is this big, then the length of the bond between those two atoms is the sum of their covalent radii. This is a hydrogen and that's a chlorine, then my hydrogen to chlorine bond is this big. Have you met bromine? Bromine's this big. In order to break a bond, I got to take those two electrons and put them somewhere. The distance between these atoms, between H and Br, or between carbon and Br, is already larger than it is between the carbon and the chlorine, or the hydrogen and the chlorine. Therefore, it's closer to being broken. Long bonds are weak. Polar bonds are weak. So my leaving group should be something big and preferentially electronegative, because I want the atoms to leave. And if I design it right, it might leave on its own. No, it's not coming from in there. Okay, so that's my reactant number one taken care of. In a substitution, you take a molecule that has a bond to X and you replace it with a bond to Y. What is Y? Well, Y is something relative. Just better. You start with the bromo, it has to be something better than bromo. So Y is here. Give me examples of things that can displace a chlorine or a bromine in a substitution reaction and make a better bond. Where on the periodic table would I look for something that makes better bonds than chlorine? To the left. Anything to the left of chlorine, well, not anything. Some things to the left of chlorine are going to make better bonds. So your atom has to be to the left of chlorine and also has to have something. Because it's the thing initiating this reaction. that leaving group is going to be pushed off. It is this reactant that does the pushing. What do I need to do the pushing? What is it in the chemical world that makes bonds? Bases make bonds, and all bases have the same thing in common. They all have lone pairs of electrons. My absolute bare minimum for Y must be is it must be something that has a lone pair of electrons and is more basic than the leaving group. I know that I'm getting more basic as I go left on the periodic table, because if I look, group 5, group 6, group 7, ammonia, it's a base. Water is amphoteric. Behaves like a base when you put it in with acid, and it acts like an acid when you put it in with base. And then hydrofluoric acid is an acid. How do I know that hydrofluoric acid is an acid? It says so in the name. And it leads with its H. I didn't write H2N. I wrote NH2. Acids lead the chemical formula with the H. So this is more acid than that, which in turn is more acidic than this. And therefore the conjugate base of this acid is a weak base. The conjugate base of this acid is a stronger base. And the conjugate base of this is more powerful still. So, moving to the left, there you go. If hydrogen always has 2 bonds. Oxygen, no, back up. Hydrogen always has 1 bond. Oxygen always has 2 bonds. If I split this water, the autoionization of water, which we saw the other day, and I take this as H plus, just the H, just the proton, none of the electrons. I take that away and have it be an acid, then I have this lone pair of electrons where one of those electrons belongs to something else other than the oxygen. That's my negative charge. When we draw the curved arrows, we often say, there's a negative, I'm just going to draw the curved arrow from the negative. You're really taking it from a lone pair of electrons. All right. Nope. That ain't it. So this notation completely disregards the fact that there are lone pairs of electrons on the oxygen and that they're doing it. If you want to be complete, you do it from the lone pair of electrons. Yeah, it's up to you. Just keep track of it. So, this reactant may have been sodium hydroxide. That's a sodium and a hydroxide, which means the sodium is just a spectator ion. It's still floating around. Yes, there it is. Are we ever going to write that down? No, not ever. We are never going to write the counterbalancing cations. They're spectator ions. They're not part of what we need to concentrate on. Okay? Strong base, good at making bonds, not acting like a base now, acting like a nucleophile. What's the difference between a nucleophile and a base?
Nucleophiles attack carbons. Bases attack hydrogens.
Nucleophiles attack carbons. Bases make bonds to hydrogen. Nucleophiles make bonds. I don't know what I'm saying. Bases make bonds to hydrogen. Nucleophiles make bonds to carbon. All right, and that's a nice little straightforward one. 2 steps, all concerted. This comes in and the leaving group leaves all at the same time. That's an example of SN2. Nucleophilic substitutions come in 2 flavors. This is the SN2. The SN2 is concerted. There are 2 curved arrows and 1 step. You replace the weak bond with the better bond, you jettison the leaving group, and it floats off somewhere else. Okay. Conditions that promote an SN2. Anybody? Yeah. Okay. It's in there. We want our nucleophile probably to be small. And negative.
So you would have to be like one set, like one hydrogen attached to that carbon. Or no?
Do I need what?
Never mind.
Is hydrogens on the carbons?
No, hey, I didn't say anything.
No. That sounds like an elimination thing. Is heat a factor? No. Is solvents a factor? Yeah. What's my preferred solvent? Polar and aprotic, like acetone. We want our nucleophile, which is this small, negatively charged thing, to not be encumbered by the solvent being excited to see it. If you put a point charge in solution and your solution is protic, meaning it can make hydrogen bonds, then you will generate a big solvation sphere around your charged reactants. And that's going to slow this reaction down. We don't want that. So, has to be polar, so that we can live with this polar molecule and that polar and ionic, really, fragment. So there you go. All right. Any preference for what the nucleophile should be? Got to keep your this molecule, your reactant. Got to keep that small. Primaries are better. Metals are good. Metals are even better. Metals and primaries better than secondaries. Tertiaries, no thank you. Tertiaries are too big. Oh, never mind. Now, if I set my conditions up right, that's a weak bond, and it's polar. And maybe, if I just wait long enough, it'll leave on its own. What could I do to help that leaving group leave? Change the solvent. Put the solvent into something protic now, something like water or alcohol. And now all of a sudden, that negative charge is surrounded by all of these little molecules wanting to show off their capacity to hydrogen bond and make a big solvation sphere. And that's just the primary one, because now all the oxygens of the waters are on the outside of that, and so there's even a secondary solvation sphere around this. And before you know it, that bromide is completely encapsulated by solvent molecules and is drifting off somewhere else in the flask. That first step is solvolysis. That's the slow, difficult step in the SN1. And the way that we help that happen is we design the haloalkane to be the best possible haloalkane that it can be. A tertiary would be nice. That would be better than the secondary. And primaries are not going to be any good because this has to be a carbocation. And primary carbocations are no good because they don't have enough carbons inductively pushing negatives at them to be stable. All right, I've got my carbocation. Let's go ahead now and make the same product, only now my second reactant, instead of being a strong base, is the weak base. And all you need to be a base or / nucleophile is a lone pair of electrons. So I'm going to get extra steps First one is in equilibrium, the other ones have a very slight push, because ultimately this is oxygen is a better base than bromide, and so we do gradually get this product right here. Oxygen uses its lone pair of electrons to reach out and grab that positive. But oxygen already had 2 bonds. It just made a new one. That means it now has 3 bonds. And an oxygen with 3 bonds has a positive charge. So we need to account for that. Going to take the electrons that are in that oxygen as a hydrogen bond, and it probably just gets swooped up by another molecule of water. Just passes by and picks it off. And now in the SN1, you have to account for it. That H plus, because you didn't use a charged, so the sodium isn't there anymore. Because we didn't use sodium hydroxide, we used HOH instead of NaOH. We now have a bromide and H. Okay? That's it. That's everything that we did. There's all the reactions that we did. Substitutions, eliminations, additions. Recognize what you've got, and there's a point when we pick up doing synthesis again, where it says go from here to here to here. You say, well, I don't know all those 2 things. Yeah, but you know enough to figure out backwards from the outside in and from this outside in, because it's giving you, starting with an alkene. Well, the only reactions we know of alkenes right now are electrophilic additions. So I'm going to take that electrophilic addition and do an addition to it. I'll take that alkene, do an electrophilic addition to it. I'm going to make something. I don't know, maybe an alcohol or a haloalkane. And then I look at my product, and my product is also an alkene. Well, how do I get from a haloalkane to an alkene? Well, that's an elimination. I just figured out what my problem is. So, start to look at the reactions in terms of what you start with, what you get, and then what do I need in the middle to make that happen? But it's, what are the conversions? Because up to this point, we only know 3 things. We know nucleophilic substitutions, electrophilic additions, and eliminations. That's going to change. It's going to get larger. But still, a class of molecule does a class of reaction. And we should be able to exclude multiple possibilities from consideration just by saying, well, I know that if you're asking me to take an alkene and turn it into something else, well, I know that's not a substitution, because alkenes don't do substitutions. And I know it's not an elimination unless you're asking me to build another double bond in there. So figure out where to go. Okay, question about Fisher projections and redrawing them. Fisher projections are written this way, specifically without the atom label. If I'm nice enough to tell you that the atom at the center of that cross is a carbon, this is no longer a Fischer projection. It's now a Kekulé structure, and Kekulé structures do not have the implied stereochemistry that a Fischer projection does. In a Fischer projection, the vertical bonds point away from you, and the horizontal bonds point towards you. So, let's put some groups in. What do you want here? I'll give you 4 different groups. And here. And here. All right. Is that the R or the S? Prioritize the groups attached to the chirality centers in order of descending atomic mass of the atom that is directly attached to the chirality center. That means that this carbon, number 1, that chlorine, I'm saying lots of words wrong today. I've been busy. That chlorine is number 1. These 2 carbons are in a tie. But this carbon is only bonded onto hydrogens, which all have a mass of 1, whereas this carbon is bonded to another carbon. So when you're at a tie, look to what they're bonded to. Here we go, 2 and 3. So 1, 2, 3, my priorities descend clockwise, and clockwise is an R, rectus, right-handed, and that is true if bond of lowest priority is pointing away from you. And it is, because the bond of lowest priority is a hydrogen, and that hydrogen is in a vertical position, so it is pointing away. Okay. Here's the same molecule. Or is it written down on a different part of the page? This is 1, 2, 3, 4. 2-chlorobutane. And we have just described that it is the R enantiomer. This one right here. Is this the same molecule? Is it a structural isomer, meaning configurationally different? Take a bond off, move it around somewhere, put it back on. Or is it the enantiomer?
The same.
How'd you know?
Just switch.
How'd you know?
You can do a double version.
What I would do, I would redraw this to match that. And I do that by taking any 2 groups. Which 2 groups do you want?
H and CH3.
If I take those 2, two groups. I am going to invert this molecule. That's the S isomer. But that is not the same, still, quite representation as this. To make that into that, what do I do? Switch two groups.
Cl and methyl.
If I switch those two, to get to here, I've done another inversion. And two back-to-back inversions is a retention. So this is still the R. Those questions that say, here are two drawings of similar looking molecules. Tell me what their relationship is. The safest thing to do is to write them down using the same notation. If they're tetrahedra, make sure they're both written as tetrahedra. If they're Fisher projections, write them both as Fisher projections. If one's a tetrahedron and one's a Fisher projection, change one of them. I know what my preference is. Doesn't necessarily have to be your preference. Okay, let's introduce a second chirality center. And see what we get. What goes here?
Hydrogen.
Oh, that was a mistake. What goes here?
Hydrogen.
Let's see. She knows what she's doing. If you sit close to her for long enough, you'll figure out what's going on. Don't worry. Okay. One of the things that we do, scan the question first and say, does my reactant have its own plane of symmetry? No. That's a chirality. First of all, are these two chirality centers? 4 different groups around that one? Yeah. 4 different groups around this one? Yeah. Okay. That represents this. Oh, I gotta make sure I'm doing it right. What's the relationship between these two molecules? Now, these two molecules can be structural isomers. I tried to draw them correctly, but hey, I may have made a mistake. I might have detached something and put it in the wrong place and actually made a configurational isomer. Chances are though, because this has 2 chirality centers, that has 2 chirality centers. It's either the same thing, or they are enantiomers which is the specific case when this molecule and that molecule are mirror images of one another, or the other most highly likely possibility, the diastereoisomers. That I have two chirality centers, and in my new molecule, one of those chirality centers is the same and the other one is different. That's statistically the most probable answer. And I wrote it down pseudo-randomly, so probably the right answer. But we should go figure it out, because I don't know what the answer is. All right. They've got to put them in the same notation. And the start for that is to just take this and renotate it this way. I want those to be vertical. Fisher projection has the horizontal bonds pointing out towards you, up, and then the vertical bonds pointing down. So, vertical bond is pointing down, that's a methyl, that's a chloro, that's a hydrogen. This is a methyl, that's a hydrogen, that's an ethyl. Okay? Now, can I rotate one of these structures so that it lines up with the other structure? I'll wait for you to catch up. What would you rather do? Would you rather redraw that one to make it match this shape, or would you rather redraw this one to make it match that shape? Just redraw this one to make it match that shape. That's probably the better answer, because every time you redraw something, there's a chance that you screw it up. And this one was written down on the exam page for you. So you've already redrawn this one, and then you redraw that one as well, there's a chance you're going to screw them both up. And unless you screw them both up equally and opposite, and luck out that you've got the correct answer, then, yeah. Okay, so I am going to redraw this one by rotating the bonds, conformational changes, and make it happen. Oh, all right, so here's what I do. That chloro is currently in the same place as this chloro. But the methyls and the hydrogens have switched places. And when you switch any two groups, what happens to your chirality center? It's inverted. That group and this group have stayed where they are. Yeah, this one's rotated, it doesn't matter. That carbon and that chloro are in the same place. Those two, these two, have switched positions. So that top one has been inverted. All right, now what I have to do here is take this methyl that is here, currently at 2 o'clock, and I'm going to rotate it up to 12 o'clock so that it matches this picture here. When I do that, this hydrogen has moved to here. This ethyl has moved to here. And now we can see that the methyl and this carbon are in alignment, but that ethyl and this hydrogen, they don't line up either. So let's write it on the other one. I have inversion at both carbons. Both of them. Okay. So what I could do, there's an additional step that you can do that might make it feel a little bit better. Take that methyl and move it to here. That takes this chloro and moves it to here, and takes that hydrogen and moves it to there, and then you get to see this. So I already know what my answer is, but now I'm going to draw it in a way that it's actually clear.
Why can't you just reverse the hydrogen and the ethyl group?
Okay. From so I'm going to rotate around this. I'm not 100% sure. Can't just move them. What's the relationship between these two molecules? That's a chirality center. That's a chirality center. What is this in relationship to that? It's the mirror image. And what's the relationship of this to that? I've inverted both chirality centers, and therefore this molecule and the other molecule are enantiomers. I knew what the answer was part way through, but then if you continue to realign these things, it makes it a little bit easier to see.
Yeah, one Monday.
Well, if you still have an issue, we can work through it.
So you can turn it on Monday. Yeah, I don't know if I
Oh.
maybe just didn't write down the stuff.
Cool.